All right, can you guys hear on Zoom now? Okay, good. Sorry about that. Yeah, every other day the microphone switches to something else and something. So yeah, thanks for letting me know. Anyway, so today we're going to be continuing with Laplace and solving differential equations. We're bringing back an old friend, probably something you haven't seen in many years, which is partial fraction decomposition. So we'll kind of refresh our memories with that. Maybe be a little bit traumatic going through that, but you're going to see that we're going to need it for our to solve ODEs with Laplace. Okay. All right. Any announcements? So you guys turned your homework 2 end of last week. Your homework 3 is just about ready. It actually is ready. I just forgot to post it today. So I'm going to post your homework 3 basically when I get to my office later this evening. So I teach another class right after this, but then after 7 o'clock, the homework 3 should be up. It's all about Laplace, and so today is actually good timing because after today, I think you should be able to do a fair bit of the homework. Okay. All right. Any questions I can answer before we get started for today? Okay. All right. So let's go and get started. And so topic for today is we're going to be solving ordinary differential equations with Laplace transforms. Okay. So let's just very quickly review what a Laplace transform is. So remember, a Laplace transform, we've been talking about it for the last couple lectures. It's an integral transform that basically transforms the function from one variable to another. Okay. In particular, we're going to be transforming a function from what we call the physical domain, which are functions of x, functions of t, into what we call the Laplace domain, which is a function of s. Okay. So we have some function of t, and we perform the Laplace transform. Okay. And then this transforms the function into some function of s. Okay, so this is usually the notation that I use. So for physical domain functions, usually I'll use a lowercase letter to denote the function. So we have little f of t, and then once we perform the Laplace transform, it's going to be basically I use a capital letter, so it's capital F of s. Okay, and notice the change of variable from t to s. Okay. So to perform a Laplace transform, you can use the formula. So there is an integral formula that you can plug in. But traditionally, the way that we do this, the way that we do it kind of quickly, is we use a table of Laplace expressions. So I'm not going to write the table down again. Was kind of a few days ago. Just because that's also a lot, but just know that typically the way we perform transforms is we kind of manipulate the function until it looks like something in the table, and then we just automatically just plug in the transform from there. Okay. Note that sometimes you do have to apply shifting. Right. So remember, shifting is something that we talked about last Thursday. Okay. Basically, with shifting, if you multiply a function in the physical domain by an exponential, so e to the at, then that's going to shift your transform in the Laplace domain by a fixed amount. Okay. So just be aware of that sometimes. So, the way that we typically do transforms is we first look at the table. If nothing matches exactly with the table, we'll see if we can use shifting to kind of help with that. And then, we do the transform from there. And for most functions that we're going to be dealing with, especially as, for engineering systems, this is good enough, right? So, very rarely do you have to actually plug in the actual formula itself. Okay. And the same can be said about inverses too. So when you're taking inverse Laplace transform, we typically use the table along with the shifting rules in order to perform our inverses. So, almost never. So there should never be a point in time in this class where you have to actually plug in your function into that integral expression. You should just be able to use the table for everything. Okay. Okay. Good. And so we are just about ready to start applying this to solve a partial or an ordinary differential equation. So Laplace transforms can be used to solve ordinary differential equations. And there's kind of one main reason why we would do this. The main reason is that it takes your ordinary differential equation and transforms it into an algebra problem that we can work out with algebra. So the typical game plan or the typical strategy for solving an ODE with Laplace transform kind of follows this kind of methodology here. Okay? So step one is to take your ordinary differential equation and take the Laplace transform of the entire equation. Okay. So I think we did this maybe at the very, very end of class last time. But we'll see it again today. Okay. Remember at this stage, you're going to be taking Laplace transforms of derivatives. And so remember to kind of take those into account as well. In particular, when you take a Laplace transform of derivative, we're going to factor in the initial conditions into that transform as well. Okay, so just kind of make sure that you take that into account. Okay. Okay, so after you take the Laplace transform of the entire ordinary differential equation, you're going to have an algebraic expression. Okay. So step two in this process is to solve for the solution using algebra, okay, within the Laplace domain. So what you're going to see is that after we take the Laplace transform, all of the derivatives are going to go away. We're just going to have an algebraic expression, and so we can just solve for it that way. Okay. It's at this point where you usually have to simplify your expression using partial fraction decompositions. Okay. And don't worry, we're going to be doing a very long, extensive review of partial fraction decomp. So, if you forgot it, don't worry, we're going to review it today. If you forgot it enough to the point where, like, you could say I've never seen it before, that's fine. We're gonna teach partial fraction decomp from scratch. Okay. And then once you have that, then the last step in this process is to just simply take the inverse Laplace transform to transform your solution back into the physical domain. Okay. So that's the game plan. It's a three-step process. You're probably going to be spending most of the time in step 2, but this is kind of the idea of how to solve an ordinary differential equation with Laplace transforms. Okay. All right. Any questions on this before we start jumping into some examples? Okay. All right. So let's start with a simple example. Okay, so we're going to solve this differential equation using Laplace. Okay, so we have y double prime minus y is equal to t. Okay. And we have the following initial conditions. So we have y of 0 is equal to 1, and then y prime of 0 is equal to 1 as well. Okay. Okay. So this is an equation that we don't need Laplace to solve this, and so you could definitely solve this in a more traditional way. So you can use your characteristic equation, solve the roots of the characteristic equation. We have a non-homogeneous term here, so you have to use undetermined coefficients, solve for the particular solution, put it all together, apply the boundary conditions, and then solve for that. So you can definitely do that. But let's see how to solve this with Laplace transforms. Okay, so let's apply our three-step process that we have up here. So step 1. Step 1 is to take the Laplace transform of this entire equation. All right, so we're going to take the Laplace transform of everything here. So we're going to take Laplace transform of y double prime minus y is equal to t. Okay. All right, so remember, Laplace transform is a linear operator, so that means we can take the Laplace transform of each term individually. So we're going to have the Laplace transform of y double prime minus Laplace transform of y is equal to Laplace transform of t. Okay. Okay. All right, so now we can take the Laplace transform of each of these individually. Okay. Notice, and just note that y here is the unknown, right? And so when we take the Laplace transform, we don't know what that is exactly, but we can we can substitute Laplace expression for it. Okay, you'll see what I mean in a second. So let's start with the Laplace transform of y double prime. So this is a second order derivative. Okay. The Laplace transform of this is going to be s squared y of s minus s y of 0 minus y prime of 0. Okay. All right, so notice, we don't know what the Laplace transform of y is, so I'm just leaving it as a generic y of s. So that's what we're going to solve for, through the algebra that we're going to do after this. Okay. Okay. Next, we have a minus sign. Then we have a Laplace transform of just y by itself, so no derivatives here. So this is just going to be y of s. Okay. And then finally, we have the Laplace transform of t. Okay, so this is something that's in the table. Okay. So that's something we can look up. And so if we look it up, then the Laplace transform of t is 1 over s squared. Okay. Okay. So we've done step one. So step one is just simply take the Laplace transform of each term. Before we move on to step two, let's go ahead and plug in the initial conditions because we have use a different color. So we have y of 0 here. We know from the initial condition that y of 0 is just 1. So let's go ahead and plug in for that. So we have s squared y of s minus s times 1. So s times 1 is just s. Okay. The other initial condition that we know is we know y prime of 0. Y prime of 0 we know from the problem is also equal to 1. Okay. So if we plug that in, we get minus 1 minus y of s is equal to 1 over s squared. Okay. All right. Any questions on how we got to this point here? Okay, good. All right. So now that we've taken the Laplace transform, we've plugged in the initial conditions. Let's move on to step two. So step two, we're going to use algebra. We're going to use algebra to solve for y of s. Okay. So basically, we're just going to isolate y of s by itself, and we're going to move everything else to the right-hand side of the equation. Okay. All right. So first thing I'm going to do is I'm going to add an s plus 1 to both sides. Okay. So that's going to get rid of that term. Other thing I'm going to do is I notice that we have y of s on these two terms here. So I'm just going to factor those out from each other. Okay. Okay. So on the left-hand side, we have s squared minus 1 multiplied by y of s. Okay. This is equal to s plus 1 plus 1 over s squared. Okay. And then to fully solve for y of s, we're just going to divide both sides by s squared minus 1. So that's going to isolate y of s on the left-hand side. And so we do that, we get y of s is equal to s plus 1 divided by s squared minus 1 plus 1 over s squared times s squared minus 1. Okay. Okay, good. So we've used algebra, we've solved for our function y or solution y in the Laplace domain. And so finally, step 3 is to just take the inverse Laplace of this expression. And so that's going to get us our solution in the physical domain. Okay. So we're basically going to take both of these terms here and then try to match them up with something in the table to take the inverse Laplace. Okay. Okay. So let's do that. So, usually at this point you have to perform a little bit extra algebra to kind of manipulate these expressions. Because if you look at the terms that we have here, neither of those terms are really something that are in the table itself. with the exception of the first one. So the first one, you could probably find that in the table. The second one, we're gonna have to work on that term a little. Okay. Okay. So for this first term here, I'm actually gonna do something a little bit clever. Okay. So I'm gonna take advantage of the fact that the denominator is s squared minus 1. So whenever you have, s squared minus another square, then you can break that up into s plus 1 times s minus 1. Okay. So we know that s squared minus 1 is equal to s plus 1 times s minus 1. Okay. And that relationship is a squared minus b squared. So whenever you have a difference of two squareds like this, okay, then this always factors into a plus b times a minus b. Okay. So it's one of those kind of useful mathematical identities that you should kind of have in your back pocket. Okay, so if we simplify that, so then that first term, so we have y of s is equal to s plus 1 divided by s plus 1 times s minus 1. Okay. We can't really do anything to the second term at this point, so I'm just going to leave it as it is. Okay. So the second term, we still are kind of maintaining this 1 over s squared times s squared minus 1. Okay. All right. With that first term there, hopefully you see that we can simplify this. So we have an s plus 1 up top, we have an s plus 1 on the bottom, and so those two are going to just cancel each other out. So you have s plus 1, s plus 1. Both of these are just going to go away. And so what we get after doing that is y of s is equal to 1 over s minus 1 plus 1 over s squared times s squared minus 1. Okay. Okay, good. All right, and so that first term there, we can go ahead and invert it because it's something that's in the table. Okay. So when we invert this term, okay, we get e to the t, right? Because in the Laplace transform of an exponential function, just 1 over s minus whatever the exponent is. Okay. And so we're Gucci on that first term. The second term, on the other hand, is kind of a mess. So if you can look at the table all you want, and you can try to look at it forward, backward, upside down, sideways. There is nothing in the table that looks like this. So there's nothing in the table that has 1 over s squared and s squared minus 1. Okay. So we're kind of stuck here. And so, at this point, we're not able to invert this, at least directly, but we can still work on this algebraically. Because if you look at the structure of this function right here, you see that, we have basically 1 over s squared multiplied by 1 over s squared minus 1. So this kind of almost seems like a multiplication of two expressions that we do have a table expression for. Okay. It would be really nice if we could actually break this up into separate fractional terms. Okay. And so in other words, what if we take 1 over s squared times s squared minus 1? Okay. What if we broke it up into one fraction that's 1 over s squared plus another fraction that's 1 over s squared minus 1? Okay. Because if we look at these individually, so we have 1 over s squared, that is something that is in the table. right? So that's just the Laplace transform of t. And if we look at 1 over s squared minus 1, we have that in the table as well. So that is the inverse of hyperbolic cosine, okay? Or the Laplace transform hyperbolic cosine. Okay. So it would be great if we can basically decompose this fraction into kind of its component parts like this. Okay. And we can do this. And so there's a reason I left the numerators blank here. Because in order to decompose this fraction, we have to solve for the corresponding coefficients up on the numerators, so a and b. Okay, so this process of decomposing a fraction is called partial fraction decomposition. And so, we're going to spend some time today just kind of reviewing, partial fraction decomposition. Okay. But are there any questions up until this point? Does this kind of make sense? Kind of, why we kind of got to this point and kind of why we want to do this? Okay. Okay. All right. So let's review partial fraction decom. Okay. So partial fraction decomposition, it's basically a process by which we can simplify a fractional expression by breaking it up into its kind of component parts, or breaking up its denominator, I should say, into its component parts. All right, so basically the idea is that, if your denominator has separate terms, you can basically separate them into separate fractions with an unknown coefficient. Okay. Okay. So let's do an example. Well, we're going to come back to that example from earlier, but let's do another example here just to kind of show how this all works. Okay. So for this example, let's just decompose. Let's decompose the following fraction here. So we have f of s is equal to 3s plus 2 divided by s squared plus s. Okay. Okay, so we want to break this up into probably at least two different fractional terms, so that we can take the inverse Laplace a bit more easily. All right, the first thing I'm going to do is I'm going to factor out s from both terms in the denominators. We have 3s plus 2 divided by s times s plus 1. All right, and so by factoring that, we can see that we have two components in our denominator that are multiplied by each other. Right? Okay, so we have component 1, which is s. Okay. And we have component 2, which is s plus 1. All right, so let's decompose this. And so let's break this up into one term that just has component 1, and then one current term that just has component 2. Okay. So the way to set this up is to have your original function, fraction on one side. So we have 3s plus 2 all over s times s plus 1, okay? And then for each component that you have in the denominator, you're gonna have a separate fraction on the right-hand side, okay? So our first component here is 1 over s, and so we're gonna have a term that's over s, okay? And then our other term is s plus 1. So we have another term that has a denominator of s plus 1. So we're going to add these two things together. Okay. And then in the numerators, we're basically going to take a page from our method of undetermined coefficients. We're going to have, unknown coefficients here, or unknown constants. So we'll say we'll have a on the first one and b on the second one. Okay. And so the goal for partial fraction decompositions is to solve for the values for a and b that make this equation true. Okay. Because basically we want to come up with an expression that's equivalent to 3s plus 2 over s times s plus 1, but we want to separate them into their different parts. Okay. Any questions on this so far? Okay, good. Okay, so to perform this partial fraction decomp, the first thing we're going to do is we're going to multiply this entire expression by the denominator. Okay. And by denominator, I mean the total denominator. So s times s plus 1. Okay. Okay. So let me write out the whole thing again. So we have 3s plus 2 divided by s times s plus 1 is equal to a over s plus b over s plus 1. Okay. So I'm going to take this entire expression, and then whatever is in the denominator on the left-hand side, we're going to multiply by that. Okay. So we have multiply by s times s plus 1. Okay. And so we're going to distribute that s times s plus 1 to every single term in this expression. Okay. And so we distribute that s times s plus 1 all the way through. And so on the left-hand side, we have 3s plus 2. Okay. So basically on the left-hand side, we just have a cancellation of the denominator. Okay. And on the right-hand side, we're going to have partial cancellation. Remember, each component only has one part of that denominator. Okay. And so for the a term, we're going to have a multiplied by, and so the s that's in the denominator under the a term is going to cancel out with one of the s's over there, but we're going to have that s plus 1 remaining. So it's a times s plus 1, okay, plus b. And so for the b term, we're going to have the s plus 1s cancel out, and then all we're left with is just b times s. Okay. Bs. What I think about most of the admin stuff I have to do with this. Okay. So next thing that we have to do with this expression here is we're going to group together like terms. So just like we did with undetermined coefficients, and so this should be kind of very familiar with that. And we're going to group together like terms in terms of the powers of s that they're multiplied. Okay. All right. So on the left-hand side, that is already kind of sorted. So we have 3s plus 2. Okay. On the right-hand side, we're going to look at all the terms that are multiplied by s. Okay. We have two of them here. So we have a times s, and then plus b times s. Okay. So the s terms are just a plus b. And then the other term that we have on the right-hand side are just the constant terms. So we have, we only have one, which is just plus a by itself. Okay. So I guess if you want to be technical, it's 1 times a. Okay. Just to kind of keep the formatting consistent. All right. So now that we've done that, let's go ahead and set up a system of equations to solve for a and b. Okay. All right, so we're basically going to be matching terms on the left-hand side and the right-hand side. Okay. All right, so let's look at the s terms first. And so for the s term on the left-hand side, we have just a 3. Okay, so this for all the s terms, we have 3 is equal to, and on the right-hand side, we have a plus b. Okay. And so this tells us that a plus b has to equal 3. Okay. All right, and then for the constant terms, we have 2 on the left-hand side. And on the right-hand side, we have just a. So for the constant terms, we have 2 is equal to a. All right, so now we can solve this system of 2 equations for our 2 unknowns. And so luckily we have, this is pretty simple. And so in this case, we have a is equal to 2. So that's just given to us right from the second equation. And so if you plug in this 2 into this first expression here, okay, and so we do that, we have 3 is equal to 2 plus b. And so we can solve this for b. And we get b is equal to 1. Okay. All right. And so if we do that, then after we plug those in, so after plugging in those expressions, we get the following. So we have 3s plus 2 divided by s times s plus 1 is equal to 2 over s plus 1 over s plus 1. Okay. So that is the partial fraction decomposition of that fraction. Okay. Okay. So now that we have our fraction in this form, now we can take the inverse of this, because if we look at each of these terms individually, minus the constants here, we see that all of these are in our Laplace table. Okay? So this wasn't part of the original problem. The original problem for this example was just to decompose it. But because you're going to be doing this anyway for the differential equations, let's look and see how we take the inverse of this. Okay. So let's take inverse Laplace. Using the table. Okay. So first term on the right-hand side there, we have 2 over s. And so 1 over s is in the table. So 1 over s is just the Laplace transform of 1. And so the inverse Laplace of this is going to be 2. Okay. So Laplace inverse of 2 over s is equal to 2. Okay. And then for the other term, we have 1 over s plus 1. So that's inverse Laplace of an exponential. Okay, so we have inverse Laplace of 1 over s plus 1. Okay. This is equal to e to the minus t. Okay, so if this function here were a a Laplace expression that you got from taking the Laplace transform of a differential equation, this would be your solution in the physical domain. So 2 plus e to the minus t. Okay. Any questions on how we did this? Okay. All right. So that's just a quick review of partial fraction decomp. So this is kind of the most ideal case. And so, this is a case where you can decompose things and your denominator has all linear terms. But what if terms appear in your denominator more than once, or you have kind of a higher power in your denominator? And this does happen. So this does happen quite a bit in practice. So let's do another example. Okay, so let's decompose and invert. Okay. So our f of s in this case is equal to s squared plus 1 divided by s times s minus 1 quantity cubed. Okay. Okay. This one's a little bit of a step up compared to the previous one. All right. In particular, we have the factor s minus 1. That one appears in the denominator 3 times because we have the factor cubed. Okay. And so when we decompose this, we have to account for all possible factors or all possible iterations of s minus 1 up to that third time. Okay. Okay, so what does this look like? So if we decompose this, so let's go set up our decomposition equations. You have s plus 1, s squared plus 1 over s times s minus 1 quantity cubed. Okay. So when we decompose this, we're actually going to decompose it into 4 separate terms. Okay. So the first term that we have here should be pretty obvious. So we have a 1 over s. So this is going to be an a over s. Okay. Right, so that one's pretty obvious because we have a component of 1 over s in the denominator on the left-hand side. Then we have components for the s minus 1 cubed. But remember, when you have an entry or a component that occurs more than once in the denominator, you have to account for all possible iterations. Okay? So what that means is that we're going to add plus b over s minus 1. Okay, so that is the first iteration. Second one is going to be plus c over s minus 1 squared. And then third iteration is going to be plus d all over s minus 1 quantity cubed. Okay. So that sequence of b over s plus s minus 1, c over s minus 1 squared, plus d over s minus 1 cubed, that's all possible iterations of s minus 1. Okay, so we have 4 terms that in our decomposition here. Okay, so all 3 of these terms here have to do with this. Okay. But from here, we're going to follow the exact same process we did in the previous example. So now that we've set up our decomposition, we need to basically get our system of equations to solve for A, B, C, and D. Okay. So first thing we're going to do is we're going to multiply this entire expression by the denominator. Okay. So we're going to multiply this entire expression by s times s minus 1 quantity cubed. Okay. And so if we do that, we get s squared plus 1 is equal to a times s minus 1 quantity cubed plus b times s minus 1 quantity squared plus c times s minus 1, okay, plus d times s. All right, so you're going to have a lot of things that cancel out, but just make sure on the right-hand side you don't cancel out everything, because they're, part of the partial fraction decomp is that, you're going to have some terms that cancel and some that. Okay. All right, so to complete this kind of problem here, we're going to have to expand out the terms on the right, okay, before we can group like terms. Okay. So the first one we have is a times s minus 1 quantity cubed, and so this is s cubed minus 3s squared plus 3s minus 1, okay, plus b times s minus 1 squared times s, and so that's going to be s, let's see, s cubed minus 2s squared plus s, okay, plus c times s squared minus s, and then the d term is just plus d times s, okay, and all this is equal to s squared plus 1. All right. So remember when we first started, I said, all this is algebra. Well, this is the algebra. So, you can decide or not whether this is better or worse than what we did before. Okay. All right. So now that we have this, let's go ahead and group the like terms. In terms of s. Okay. All right. So on the left-hand side, we have s squared plus 1. On the right-hand side, let's go ahead and group together everything that's s cubed. Okay. So for s cubed right here, we have 2 terms. We have just a plus b. Okay. Right. Then we have the s squared term. So for s squared terms, we have a minus 3a, a minus 2b, plus c. Okay. All right, and then for the s terms, let's see. So for s by itself, we have a 3a plus b minus c plus d. Okay. And then for the constant terms, we actually only have one, which is a minus a. So you have a plus 1 times minus a. Okay. So now from this point, we can set up a system. Now we have, it's four unknowns, and so we need four equations, okay? So let's set up our four equations here. So we have the s cubed term. Okay. And so for the s cubed on the left-hand side, we don't have an s cubed on the left-hand side, so we have 0. Okay. This is equal to a plus b. Okay. For the s squared term on the left-hand side, we have a 1. Okay. We just have s squared by itself on the left-hand side, so that means we just have 1 there. Okay. This is equal to the s squared expression on the right. So this is equal to minus 3a minus 2b plus c. Next, we have the s term by itself. So on the left-hand side for s, we have nothing. So we have just a 0. And on the right-hand side, we have 3a plus b minus c plus d. Okay, so that's probably the longest expression that we have. And then for the constant term, for 1, on the left-hand side, we just have 1. On the right-hand side, we have minus a. Okay. So we have a system of four equations, four unknowns. This one looks scary, but it's actually not too bad. We can actually solve it pretty sequentially. But you can use these equations to solve for A, B, and. All right. Any questions on this so far? Okay, good. Okay, so let's go ahead and solve this system. So on the last equation there, we can see that we have A is equal to minus 1. Okay. We see our first equation is just a plus b is equal to 0. So that means we can take this a and plug it in up here. Okay. And so we get b is equal to 1. All right. So then now we have a and b. We can plug that into equation 2. That's going to give us c. Okay. And so for c, we're going to use the second equation. We have 1 is equal to minus 3 times minus 1, which is 3. Minus 2 times b, and b is just 1, so it's minus 2 plus c. And so if we simplify this, we have 1 is equal to 1 plus c. And then we subtract 1 from both sides. We get c is equal to 0. And then we finally plug everything into the last equation here. So we have 3a, or actually we have 0 is equal to 3 times a, so that's minus 3, plus b, so that's going to be plus 1, minus c, c is just 0, plus d. Okay. And so we simplify that. We have 0 is equal to minus 2 plus d. We add 2 to both sides. We get d is equal to 2. Okay. So it's a scary system of equations, but luckily everything was kind of fairly well sequenced, and so we were able to solve for all of the unknowns there. Okay. All right. So let's plug this back into our decomp. And so we plug these coefficients back in. Let's see. So we have a over s. So a is a minus 1. So we have f of s is equal to minus 1 over s. Okay. Then we have b is equal to 1. So that's b, which is 1 over s minus 1. Okay. We have c is equal to 0. So I'm going to skip the c term. And then we have a plus d, or 2, over s minus 1 quantity cubed. All right. Good. So we've taken that kind of really nasty kind of fractional expression and turn it into something like this, where we can more easily take the inverse by looking up expressions in the table. Okay. Okay. So let's take the inverse according to the table. And so first we have inverse of -1/s. We know that this is the Laplace transform of 1 is just 1/f. And so the Laplace transform of this, or the inverse Laplace, is going to be a -1. Okay. All right, so that one's just read straight off the table. I'm not accounting for the negative, of course. Okay. Next, we have 1/s-1. This one also can be read just straight off the table. And so this is just the Laplace transform of e to the t. Okay. Right, so the first two terms, you take the inverse. Those are just very straight up. That last term there might look a little bit intimidating, but if we remember our first shifting theorem, then this one actually is pretty, pretty easy. Okay. Because what does this look like? So if you look at this term, okay, this is very similar to something that's in the table, which is 2/s². Okay. So this expression is in the table. Okay. And so it looks similar to that. Of course, we don't have that exactly. We don't have 2/s². We have 2/s-1³. Okay. But if we remember our first shifting theorem, we can basically say that this s-1, okay, this s-1 here came about as a result of our shifting. Okay. And so taking the inverse Laplace of this last term is a combination of applying our shifting theorem together with our inverse Laplace of 2/s². Okay. And so the inverse Laplace of this, first let's do the shifting. Okay. And so to kind of apply the inverse of the shifting, we have to multiply by an exponential. Okay. And so the inverse of this is going to be e to the t. Okay. So that e to the t here, this accounts for that shift of s-1 in the Laplace domain. Okay. All right, and so if we kind of undo that shift, and so we undo that shift by multiplying by e to the t, then we have the inverse Laplace of 2/s², which we do know from the table, okay, which is t squared. So this t squared here is the inverse of 2/s². Okay. And so that right there is our final inverted expression. So f of t is equal to -1 plus e to the t plus e to the t times t squared. All right. Any questions on how we got this result here? Okay. So the thing with inverse Laplaces is that, for me, I've been teaching this for years, and so I've seen this a million times. But finding the patterns and kind of matching things up with the table, it takes practice. And so don't feel a lot of kind of what we do, especially in the class, I'm doing it really quickly just because of time. But it takes a while to kind of see the patterns in these expressions and to match them up with the table. So if you're kind of struggling with this, or if you don't know whether you should apply partial fractions, or maybe you already applied partial fractions, you don't really know what to do next, don't be discouraged, and don't be afraid to ask. And so, because these things are, they take a lot of practice to see. Okay. So that was an example of partial fraction decomposition when you have a term that appears more than one time in the denominator. Okay. There's one more case that we have to go over. Okay. And this actually relates back to the first example that we were doing. Okay. Okay. And so this last case is going to basically account for situations where you cannot factor, or you cannot break up a quadratic term in the denominator. Okay. So this next example, I'm just going to do fairly quickly, just because I do want to go back and finish up that other example. Okay. But let's say we have f of s is equal to s minus 3. I don't know why I wrote 1. My mouse said 3. My brain said 1. Okay. Divided by s cubed plus 3s. Okay. And so just like we did in the last example, let's decompose this into its component fractions and then take the inverse. Okay. So first thing we see here is let's factor out a 3, or let's factor out an s from the denominator. So if we do that, we get s minus 3 over s times s squared plus 3. Okay. Right. That's good. So we kind of factored that out. And so let's decompose this into different expressions. Okay. Except we have one issue here that we haven't seen in our previous examples. It's the fact that the denominator this time contains a quadratic expression that we can't factor anymore. Right? So we can't break that down into any kind of linear term. So we can't break it down to s plus something, or s, s minus something plus times s plus something. So we kind of just have to leave it as it is. Okay. And so that means our decomposition, we have s minus 3 all over s times s squared plus 3. Okay. So our decomposition has to account for this. And so on the one hand, we were able to factor out a 1 over s. And so our first term in our decomposition is going to be a over s. Okay. And then our second term, since we can't factor that s squared plus 3 anymore, we're going to leave it as it is. We're going to leave it s squared plus 3. Okay. So that's going to be our second term in the decom. Okay. But because that denominator has a power of s that's greater than 1, and it's not a repeat, right? So I think this case compared to the previous example, I think people kind of get confused a lot. But because this is a quadratic that's not a repeat root, so this has power, or this is a quadratic term. So it's not a repeat root at the last one. So the last one we had s minus 1 quantity cubed. Even though that was an expression that was technically cubed, it was the same root. So the same s minus 1, it was just repeated kind of 3 times. So we had it cubed. Okay. So this is different. So we have a quadratic term here, s squared plus 3, but it's not a repeat root. It's just kind of a, you know, an extra artifact. Okay. And so when we break this up, our numerator here has to account for the fact that, you know, we have a quadratic denominator. Okay. And so typically we would just do b on top, right? Just a constant. But when our denominator here is some power greater than 1, and, you know, for this class, you know, you're only going to really see quadratic, you need to account for that in the numerator. So the numerator has to be always 1 power less than the denominator. Okay. And so our numerator in this decomposition is going to be bs plus c. So numerator All right, so I'm probably not going to give you any x cubed terms in the denominator there, just because that doesn't really match up with anything in the table. So the most you're going to have to do is going to be, you know, a linear function up top. So, you know, as plus b or bs plus c, something like that. Okay. Okay. Any questions on how we got this this form here? Okay. Good. So for this one, you know, I do want to get back to the example that we just did first, just to kind of close the loop on today. But from here, you know, you would just kind of follow the same process. So you'd multiply everything by the denominator, you group together like terms, you solve the system of equations, and that's going to give you your expressions for A, B, and C. Okay. So if you want to look at the solution to this example, it's in the notes. It's not too long, but, you know, we only have about 5 minutes left. And so I did want to get back to our previous example. Okay. So solution to this. So I definitely check it out. The lecture notes actually do have quite a few other examples too that I didn't have time to cover in class. So definitely check those out. You know, especially with the Laplace stuff, I think you just have to see a bunch of examples to really, you know, start getting used to it. Okay. But anyway, back to where we were before. Spell correctly. As we look back to our previous example, we had y of s is equal to 1 over s minus 1 plus 1 over s squared times s squared minus 1. Okay. All right. So that's where we started. That's the problem that we had. And what we said was that in order to properly take the inverse of that second term, the 1 over s squared times s squared minus 1, we need to perform partial fraction decomposition. Okay. So we actually have a combination of our last two examples here. So we have one term in the denominator that appears, that's a root that appears more than once, and so we have s squared. And so that one we need to account for in two terms. Okay. So we have 1 over s squared times s squared minus 1. Okay. So if we're going to break this up, first we need to break up that 1 over s squared. So this is going to be a over s plus b over s squared. Okay. So remember, that's a root that appears kind of more than once in the denominator. So we have to account for all powers of the root going up, right? So we have one a over s plus b over s squared. Okay, so this is all since s appears multiple times. Okay. So that's why we have two there, because we had s appearing twice. We have a over s plus b over s squared. Okay. And for the second part of the decomp, we have 1 over s squared minus 1. I know technically you can treat that as two separate terms, but that does technically factor. So you can have 1 over s plus 1 times 1 over s minus 1 and put those separately. But just to be kind of illustrative, just on the previous example, you're going to get the same thing anyway. Let's treat this as a term that's not able to be factored. Okay. So that means we're going to have another term here that's over s squared minus 1. Okay. So this right here is a term that is quadratic in the denominator. That's not a repeat root. Okay. And so that's just kind of like the last example we did right before this that we didn't get to finish. But what this means that in the numerator, we have to have a polynomial that's one order less. And so in the numerator here, we're going to have a c times s plus d. Okay. Any questions on how we got this expression here? Okay, so we're just about out of time. I don't want to start solving this just because we have about 1 minute left. So we'll next time on Thursday, we'll start with this example. We'll just kind of hit the ground running with this. We'll finish up this example and we'll do a couple more ODEs solving with Laplace. Okay. All right. So thank you guys for coming today. I hope you guys have a good rest of your day, and I will see you guys on Thursday. Yeah. Thanks, Joel.